All right, so now we're going to solve a non-homogeneous equation by using Laplace transform. So we're just going to get right to it. So we take the Laplace transform of each term, and then we're going to end up solving for y of s, because we know that every term that's there has a y of s in it. And then from there, we're going to be able to find our original function, which is the solution to the differential equation. So the Laplace transform of y double prime is s squared y of s minus s times y of 0 minus y prime at 0. And we have 4, now the Laplace transform of y, we just call that y of s. And the Laplace transform of the right-hand side, well, that's different this time because it's non-homogeneous. That's 5 over s plus 1. So let's see how this shakes out. Well, y at 0 is 0, so this term goes away. Y prime at 0 is 2. So we have s squared plus 4 y of s minus 2 equals 5 over s plus 1. Well, I'm just going to do a little bit of thinking ahead here, and I'm just going to say that s squared plus 4 y of s is equal to, now, I am going to make a common denominator. Well, I'm just going to write plus 2 times s plus 1, because I know that's what it's going to be. So it's 2 times s plus 1 over s plus 1, and then they combine. Because I want to be able to write y of s as a single function. That's usually what's most helpful. So the numerator becomes 2s plus 7 over s plus 1 times s squared plus 4. So gee, I wonder what happens from here. It will say partial fraction decomposition. So we're going to say that this is equal to some constant over s plus 1. Remember the tip with dealing with a non-factorable quadratic in the denominator? I tend to write it as bs over s squared plus 4 plus c over s squared plus 4. So truthfully, at this point, we kind of know what the inverse transform is going to look like. It's just a matter of finding a, b, and c. But we're going to follow suit here, and we're going to actually find the constants. So this means that 2s plus 7 is equal to a times s squared plus 4 plus bs times s plus 1 plus c times s plus 1. And it might be easier for this case to just collect like terms by powers of s. So this is s squared times, let's see, we have an a and we have a bs times s, which is a bs squared. So it's like a plus b. For the s terms, looks like we have a bs times 1 and a c times s. So we have that. This is a very interesting looking system. And for the constant, we have 4a plus c. So let's see here. So this means that a plus b is equal to 0. This means that b plus c is equal to 2. And 4a plus c is equal to 7. So let's see how this shakes out. I'm going to write everything in terms of b. So I'm going to have a is equal to negative b, and c is equal to 2 minus b. So it means we have 4 times negative b plus 2 minus b equals 7. So that's negative 5b is equal to 5, which means b is equal to negative 1, which means a is equal to 1 and c is equal to 3. So that was a nice solution. So it looks like our transform is 1 over s plus 1 minus 1s, so actually just s, over s squared plus 4 plus 3 over s squared plus 4. So now the inverse transform, which is the solution to the differential equation, the moment we've all been waiting for, the inverse transform of 1 over s plus 1 is just e to the negative t. The inverse transform of s over s squared plus 4 is just cosine of 2t. Now remember how this has to work. We're expecting a 2 up here, so a 2 down here. So that means that the inverse transform of 3 over s squared plus 4 is 3/2 sine of 2t. And there we have it. So that's solving a non-homogeneous by Laplace transform. Was that quicker than using the other method? Maybe, maybe not. But again, remember all the crazy ideas we had with non-homogeneous equations. Maybe the Laplace transform can make some of those easier. So we got more videos in the future. Thanks for watching.